I was one of those kids that every time I got in the car, I basically had to roll down the window. It was usually too hot, too stuffy, or just too smelly. And my father would not let us use the air conditioner. He said that it would overheat the engine. And you might remember, some of you, how the cars were back then, and it was a common problem of overheating. But it was also the signal that capped the use or overuse of energy-consuming devices. Things have changed now. We have cars that we take across country, we blast the air conditioning the entire way, and we never experience overheating. So there's no more signal for us to tell us to stop. Great, right? Well, we have similar problems in buildings. In the past, before air conditioning, we had thick walls. The thick walls are great for insulation. It keeps the interior very cool during the summertime and warm during the wintertime. And the small windows were also very good because it limited the amount of temperature transfer between the interior and exterior. Then in about the 1930s, with the advent of plate glass, rolled steel, and mass production, we were able to make floor-to-ceiling windows and unobstructed views, and with that came the irreversible reliance on mechanical air conditioning to cool our solar-heated spaces. Over time, the buildings got taller and bigger, our engineering even better, so that the mechanical systems were massive. They require a huge amount of energy. They give off a lot of heat into the atmosphere, and for some of you may understand the heat island effect in cities where the urban areas are much more warm than the adjacent rural areas. But we also have problems that when we lose power, we can't open a window here. And so the buildings are uninhabitable and have to remain vacant until that air conditioning system can start up again. Even worse, with our intention of trying to make buildings move towards a net zero energy state, we can't do it just by making mechanical systems more and more efficient. We need to look for something else, and we've gotten ourselves a little bit into a rut. So what do we do here? How do we pull ourselves and dig us out of this hole that we've dug? If we look at biology, and many of you probably don't know, I was a biology major before I went into architecture. The human skin is the organ that naturally regulates the temperature in the body. And it's a fantastic thing. That's the first line of defense for the body. It has pores, it has sweat glands, it has all these things that work together very dynamically and very efficiently. And so what I propose is that our building skins should be more similar to human skin. And by doing so, it can be much more dynamic, responsive, and differentiated depending on where it is. And this gets me back to my research. What I propose first doing is looking at a different material palette to do that. I currently work with smart materials and a smart thermal bimetal. First of all, I guess we call it smart because it requires no controls and it requires no energy, and that's a very big deal for architecture. What it is a lamination of two different metals together. You can see that here by the different reflection on the side. And because it has two different coefficients of expansion, when heated, one side will expand faster than the other and result in a curling action. So in early prototypes, I built these surfaces to try to see how the curl would react to temperature and possibly allow air to ventilate through the system. And in other prototypes, did surfaces where the multiplicity of having these strips together can try to make bigger movement happen when also heated. And currently have this installation at the Materials and Application Gallery in Silver Lake, close by, and it's there till August if you want to see it. It's called Bloom, and the surface is made completely out of thermal bimetal. And its intention is to make this canopy that does two things. One is it's a sun shading device so that when the sun hits the surface, it constricts the amount of sun passing through. And in other areas, it's a ventilating system so that hot trapped air underneath can actually move through and out when necessary. You can see here in this time-lapse video that the sun, as it moves across the surface, as well as the shade, each of the tiles move individually. Keep in mind, with the digital technology that we have today, this thing was made out of about 14,000 pieces, and there's no two pieces alike at all. Every single one is different. And the great thing with that is the fact that we can calibrate each one to be very, very specific to its location, to the angle of the sun, and also how the thing actually curls. So this kind of proof of concept project has a lot of implications to actual future application in architecture. And in this case, here you see a house that's for a developer in China, and it's actually a 4-story glass box. It's still with that glass box because we still want that visual access. But now it's sheathed with this thermal bimetal layer. It's a screen that goes around it, and that layer can actually open and close as that sun moves around on that surface. In addition to that, it can also screen areas for privacy so that it could differentiate from some of the public areas in the space during different times of day. And what it basically implies is that in houses now, we don't need drapes or shutters or blinds anymore because we can sheathe the building with these things as well as control the amount of air conditioning you need inside that building. I'm also looking at trying to develop some building components for the market. And so here you see a pretty typical double glazed window panel. And in that panel, between those two pieces of glass, that double glazing, I'm trying to work on making a thermal bimetal pattern system so that when the sun hits that outside layer and heats that interior cavity, that thermal bimetal will begin to curl. And what actually will happen then is it'll start to block out the sun in certain areas of the building, and totally if necessary. And so you can imagine even in this application that in a high-rise building where the panel systems go from floor to floor up to 30, 40 floors, the entire surface could be differentiated at different times of day depending on how that sun moves across and hits that surface. And these are some later studies that are working on right now that are on the boards, where you can see in the bottom right-hand corner with the red, it's actually smaller pieces of thermal bimetal, and it's actually we're trying to make it move like cilia or eyelashes. This last project is also a components. It's the influence, and if you have noticed, one of my spheres of influence is biology, is from grasshopper. And grasshoppers have a different kind of breathing system. They breathe through holes in their sides called spiracles. And they bring the air through, and it moves through their system to cool them down. And so in this project, I'm trying to look at how we can consider that in architecture too, how we can bring air through holes in the sides of a building. And so you see here some early studies of blocks where those holes are actually coming through, and this is before the thermal bimetal is applied. And this is after the bimetal is applied. Sorry, it's a little hard to see, but on the surfaces you can see these red arrows. On the left, it's when it's cold and the thermal bimetal is flat, so it will constrict air from passing through the blocks. And on the right, the thermal bimetal curls and allows that air to pass through. So those are two different components that I'm working on. And again, it's a completely different thing because you can imagine that air could potentially be coming through the walls instead of opening windows. So I want to leave you with one last impression about the project or this kind of work in using smart materials. When you're tired of opening and closing those blinds day after day, when you're on vacation and there's no one there on the weekends to be turning off and on the controls, or when there's a power outage and you have no electricity to rely on, these thermal bimetals will still be working tirelessly, efficiently, and endlessly. Thank you.